Time for a video on ionic bonding. In this particular unit, and we're working out of Unit 6 here, in this particular unit there are two types of bonding that we have to become familiar with: ionic bonding and covalent bonding. I'll start with the ionic bonding in this video, and we'll cover covalent bonding in a separate one. First, ionic bonding is what happens when metals and non-metals get together. You recall when we learned the periodic table, we talked about the dark stair-step line that runs down the right-hand side of the table. This dark stair-step line marks the location of the metalloids. The metals are the substances to the left of those metalloids, so everything over here includes these two rows on the bottom, does not include hydrogen. These substances here are metals. Non-metals are to the right. So over here on the right side of the periodic table, to the right of the metalloids, those are the non-metals. When something from the left of the table gets together with something from the right, when a metal gets together with a non-metal, they will form an ionic bond. They do so to satisfy the octet rule. The octet rule applies to both ionic and covalent bonding. It tells us the most stable atoms have 8 valence electrons. Remember, valence electrons are the electrons in the outermost energy level. There are some exceptions to the octet rule. Those exceptions are the first 4 elements on the periodic table: hydrogen, helium, lithium, and beryllium. These do not follow the octet rule. These need only 2 valence electrons to become stable. Everything else, though, requires 8. And ionic bonding is one of the 2 ways that atoms can get those 8 valence electrons. First, we'll take a look at what's going to happen to our metals. Again, our metals are the substances to the left of the metalloids. Metals are predominantly in groups 1 through 13, which means they have 1 through 3 valence electrons. 1, 2, or 3. They're less than halfway to an octet. They cannot gain enough electrons to become stable. No matter how hard they try, they will not be able to get enough electrons to fill that outermost energy level. So what they're going to have to do instead is lose what they have. The metals have to lose their valence electrons so they can lose the entire outermost energy level. When they lose that outermost energy level, the one directly underneath it becomes the new valence level, and in most cases, this new level has 8 valence electrons. It is a stable level. It will satisfy the octet rule. I compare this to a head of lettuce. If you have a head of lettuce and there's some brown spots on it, you don't throw the whole head of lettuce away. You just peel away the bad layers. This atom has a bad layer. This atom has a layer with a brown spot, that 1 valence electron. If we want to make this atom good, we do what we do with the lettuce. We peel away the bad layers. We take that bad layer away. Underneath it is a nice stable one. For the nonmetals, we're dealing with 5 through 7 valence electrons. The most reactive nonmetals are in groups 15, 16, and 17. 15 would have 5, 16 would have 6, 17 would have 7 valence electrons. They're over halfway to that octet. They can gain what they need in order to become stable. And that's exactly what they're going to do. They're going to gain enough electrons to become stable. This is an oxygen atom. I know it's oxygen by counting up the number of electrons. I have 1, 2, 3, 4, 5, 6, 7, 8 electrons. My protons and electrons should be the same. So if I have 8 electrons, I should have 8 protons. I whip out my handy-dandy periodic table, look up atomic number 8. That's oxygen. This is an oxygen atom. Oxygen's in group 16. I know that too by the valence electrons. 1, 2, 3, 4, 5, 6. Valence electrons tells me it's in group 16. The 2 energy levels tells me it's in period 2. So again, I can look at my periodic table. Period 2, group 16 is oxygen. That's another way that I can identify what element this is. So this is my oxygen atom. 6 valence electrons. It needs 8 to be stable. So what my oxygen must do is gain 2 more. And if it gains those last 2 electrons, now we'll have 8 in our outermost energy level. 1, 2, 3, 4, 5, 6, 7, 8. Everything's happy, everything's stable with this. Now when these metals and nonmetals get together, when those metals give away their electrons, when those nonmetals take those electrons, it's going to throw the charge of our atom out of balance. They will become ions. Ions are the name we give to charged atoms. Metals will become positive ions. Nonmetals will become negative ions. Just like in the previous video where we talked about protons and electrons, we talked about things with positive and negative charges before. Those opposite charges will attract each other. And that's going to end up being our ionic bond. Let's take a look at where that charge comes from. In sodium, our neutral sodium, the periodic table type sodium, it's atomic number 11. It means it has 11 protons, and the neutral atom will also have 11 electrons. We can think of this as positive 11, each proton being a positive charge. We can think about this as being negative 11. Every electron is a negative charge. What happens when you add positive 11 and negative 11 together? Yes, indeed, they cancel out. That is the neutral atom. No charge. For the ion, we have lost 1 electron. That picture that I had up there, that diagram that I had up there is sodium. We still have 11 protons. We haven't done anything to the nucleus. We've taken 1 of its electrons away. So instead of having the normal 11, it now has 10. Again, we can think of that as positive 11, each of those protons being a +1 charge. We can think of this as being negative 10. Again, every one of those electrons being a negative 1 charge. Now when we add it together, no more 0. Positive 11 plus negative 10 gives us positive 1. This is the charge of the sodium ion. It is a positive ion. It has a charge of +1. We look at our nonmetal. Oxygen, as I mentioned, was the example that I gave you for our nonmetal. Looking at the periodic table, it has 8 protons. The neutral atom should also have the same number of electrons. Again, each proton counts as a +1, so we have a total positive 8 charge there. Every electron counts as a negative 1, so we have a total negative 8 charge there. Positive 8 plus negative 8. No surprise, it's a neutral atom. The charge is 0. When we made that oxygen ion, we added 2 electrons to that atom. We gained 2 electrons. So instead of the normal 8, our ion has 10. Still 8 protons, so it's still a +8. 10 electrons, again, each one is a negative 1 charge. Negative 10. Positive 8 plus negative 10 is negative 2. That is the charge of our oxygen ion. Our nonmetal has a negative charge. When these things get together, it's just, again, like the protons and electrons. Protons are positive, electrons are negative. They're attracted to each other. That's what keeps the electrons near the nucleus. Here we have a positive metal and a negative nonmetal. They'll be attracted to each other as well. They'll want to stick together. That attractive force is called an ionic bond. That is what holds those 2 ions together. That is what makes our compound. That's what joins the atoms. That's what causes them to no longer be elements. That's what makes the compound, that attractive force. Now we have a charge on our atom. We have to show that with our symbol. We wouldn't just want to write down Na. If I wrote down Na, you'd think it's the periodic table atom. You think it's that average atom. If I want you to think ion, I put this +1 charge on it. And the charge is always written in the upper right-hand corner. If I wanted you to know I'm talking about an oxygen ion, not the plain old average neutral atom from the periodic table, I'll put that -2 charge in the upper right-hand corner. Whenever you see these, you know you're dealing with an ion. Now I will warn you, some people write 1 plus or 2 minus. They'll flip the sign and the number. They mean the same thing. Sometimes that 1 will be missing altogether. If you don't see a number in chemistry, always assume it's a 1. You have to be able to write the formulas for these compounds. And formula writing is all about finding neutral ground, finding a compound that has no overall charge. In this case, with my sodium and my oxygen, I have a +1 charge, I have a -2 charge. Those don't cancel out. We have to make these charges cancel. We have to make the total charge 0. So where I have a -2 over here, I'm going to need a +2 on this side. And the way I do that is by having 2 sodiums. When I have 2 sodiums, my total charge over here is +2. My total charge over here is -2. And those cancel each other out. And my compound will be neutral. To write this formula, I write the symbol of my metal first, Na. There are 2 of them, so I put that subscript 2. Then I write the symbol for my nonmetal. There's only 1, so I leave this blank. It's like H2O. You know there's 1 oxygen, even though there's not a 1 there. We know there's 1 oxygen here, even though there's no 1 written down. Na2O would be the formula for this compound if sodium and oxygen were to combine together. And again, it's about making these charges cancel out. Do another example for you. Magnesium and chlorine. Magnesium is a +2, chlorine is a -1. Those don't cancel out. In order to cancel out, we're going to need a -2 over here. To get that -2, I'm going to need another chlorine. Now my total positive charge is +2. My total negative charge, -2. Those cancel out. To write the formula, again, I start with the metal. There's only 1 of them, so we leave it blank for the subscript. Then I write my nonmetal. There are 2 of those. Subscript 2 to show that. Again, it's all about charge cancellation. In physical science, you will not have to worry about anything more than this. +1s and -2s, or +2s and -1s. Some cases they'll naturally cancel out like they do here. Beryllium is a +2, chlorine is a -2. When they cancel out like this, you just write down the symbols. Again, the metal is always first. BeO. On the periodic table that I keep in front of my classroom, I have something called oxidation numbers. If I pan over to this table, you can't really make them out on the video, but you can see these yellow numbers that are written on top of the groups. This tells us what the charge on these ions will be. I can know beryllium is a +2 because if I find it on the periodic table, go to the top of this group, I can see the +2. I can know oxygen is a -2 again by finding it on the periodic table, going to the top, and seeing that -2 there. I'll cover those oxidation numbers in class, and the best bet there is just to memorize them. As usual, if you have any questions, make sure that you ask me in class or leave me questions on the wall. We'll cover covalent bonding next.